Hi, this is part of my final managing machine learning project for Coursera. Okay, so let's look at the opportunity. So in this problem, I will try to use machine learning to solve for FMCG companies in India. Now, FMCG companies sell fast-moving consumer goods like, soap, toothpaste, your daily needs kind of things. And in India, there are millions of small mom and pop stores uh, which provide customers or which are like the last endpoint for customers to buy these products. Now, currently FMCG companies like Britannia, Nestle, uh, they rely on a large network of distributors who refill these small mom and pop stores on a daily basis uh, to ensure that they are well stocked with the product. Now the current process is that these big companies provide their goods to the distributors who then replenish all the shops in their area on a daily basis. So they have a van that goes out in the morning and replenishes all the shops in its area. And since the demand from these small shops are like very volatile because they serve small localities, uh, the route is quite long and they have to deploy multiple vans in their area to replenish the shops every day. Now, and sometimes because of this, they incur charges for transportation. And if the shop is not stocked properly, it can also lead to stock out, which is like uh, if someone's looking for bread, the item's not there, they'll probably go to a different shop and buy it. So it also leads to loss of sales. So let's look at our goals through the CRISP TM business understanding framework. So what we want to use machine learning here is to sort of predict which shops will undergo stockouts 24 hours in advance uh, based on their uh, based on their uh, based on their sales, weather, and other data sources. Now, what this will allow us to do is that if we can accurately predict in advance which shops will have a stock out, we don't really need to send out the van to replenish all the shops in the network. We can only send it out to the shops that are part of this that are going to have a stock out, and in that process we will end up saving on transportation cost because otherwise the van just sort of go to the entire route. And since we will be able to forecast supply in time, we can also make sure that based on the demand for different products, we can supply the shop with the exact right items. So let's assume that if there was one day uh, when it's forecasted because of hot weather or something like that, we expect to sell more number of cold beverages. We could provide the shop with extra units of those things to ensure that the stock does not go out. So let's look at data understanding. So our model will primarily use sales data from the stores at a daily level, which we already have at a historical basis for us, along with weather forecasts, because the kind of weather, extremely hot or extremely cold, can have an impact on which items sell more, and other events like festivals, which can also impact demand. So this data, first of all, the sales data will be extracted from the company's ERP system because they are daily replenishing these stores. So they have a good database of daily sales volume over there. And data for weather and festivals and other kind of events that we'll be looking at will have to be obtained through third-party vendors or through open sources. Now, coming to the modeling part, the modeler will simply be a classifier which will identify stores that are about to experience a stock out in the next 24 hours. So it can start off with something very simple like logistic regression, and move to more complex model like decision trees as the model becomes more mature. Now, successful uh, evaluation criteria for the model will be how accurately it can uh, how accurately it can determine stockouts, and if this project gets successfully implemented, we will reduce transportation costs as only stores which are facing stockouts will get refreshed or replenished, and will get replenished, saving transportation cost, and there will be less sales lost due to stockouts. Now, the model will be successfully deployed only when it achieves at least 90% accuracy, or otherwise, the benefits that we get from savings in transportation costs may just get offsetted by stockouts that occur on stores where stockout occurs when it is not being forecasted by the model. Now, model validation will involve validating actual stockouts in the shops where the model predicts there is a stockout. So essentially, we'll be looking at the ROC curve, looking at true positive rate and false positive rate to ensure that the ROC curve is at least zero point 0.9, or at least in 90% of the cases where the model predicts a stockout will occur, it is occurring, and there'll be fewer cases where the model does not predict a stockout and there ends up being a stockout. So we'll be tracking these false negatives and false positives because, as I said before, if the shop is not replenished, there'll be a stockout, and whatever we save in transportation will have to be compensated through lost sales. So both of these factors will have to be taken into account. Once the model is evaluated at a satisfactory level on both of these criteria, it will be rolled out. And even for the rollout, we will not roll it out on the entire network at once. It will be rolled out through a small test population, and we will be looking at cost savings as compared to the normal method where the van goes to all shops every day. And only if the savings make sense will we move ahead with the model. So the model testing will run for at least 2-3 months, and uh, on satisfactory results of the model on all of these nodes, uh, it will be rolled out to all nodes on the system. So based on the above requirements, let's see how our ML system design will look like. So because sales data and climate and all those kind of things need not happen on a device. They can happen more efficiently on a cloud. So we will prefer a cloud-based system. So this will be more effective because cloud is already built to take care of large data sets and has a lot of features built in to allow us to work with this kind of data. Next, it will also be more cost effective as compared to a non-cloud based or edge based or on device solution. Next, the kind of learning, since latency is not an issue, the data or the model can be created just once, so connectivity will not be an issue. And since the company owns all the sales data that comes from the from the ERP, we are not concerned about that. And since the model need not be updated every time a sale is made, so offline learning will be more suitable for this project as compared to online learning. And we will require batch predictions since there is no need to since the predictions only need to run once a day to predict which shops are going to have stockouts in the next 24 hours. We don't really. So let's look at potential risks in production. So the first risk for this model is concept drift. So since the forecast is going to be based on past sales, any change in people's preferences for products can have an impact on accuracy of the model. And the other thing that's happening here in India is that these small shops mom and pop stores at neighborhoods are being slowly losing market share to e-commerce websites like Amazon. So over a longer period of time, that can have an impact on sales, and as it'll have an impact on sales, it'll also have an impact on how well our model can forecast the stockouts for these shops, because the usage of these shops will go down. And the last thing is that, these shops are not really owned by the FMCG companies. So the store owner, uh, for the store owner, the FMCG company is just one of the suppliers for biscuits and the other goods. So let's assume that, uh, you are Pepsi and you are selling your drinks through this particular shop, and the shopkeeper gets a higher margin through Coke. So he could end up stocking both Coke and Pepsi products on his shop, and this can have an impact on your Pepsi sales, right? And the storekeeper need not even let us know that he's doing this. We'll only be able to see a drop in sales for our product here. So that is also another big risk that can have an impact on performance of the model. Now, the second risk for this project is cost savings. So, as we said, right, so our system will lead to cost savings only because of transportation cost, because the van need not go to all shops. And the next thing is that it will correctly predict, or there'll be very few cases where a stock that has not been predicted to have a stock out actually experiences a stock out. So, and given both of these things, the model uh, will have to have enough cost savings over a period of time to justify the investment and investment in maintaining and having the system implemented. So that could be one of the things that, the model is maybe initially very good, or the cost savings that are generated from the model are just not worth the trouble of making all the changes to the network. And a simpler network with the van goes to all shops is more suitable in this case. And the last thing is sort of lost sales. So if the model does not predict stockouts correctly, the shops where the forecast does not predict a stockout can have a stockout, and whatever savings we have through transport could be lost through stockouts occurring in shops where a stockout was not predicted. So, bearing in mind these production risks, we will have to lead this project and see how we can best use it uh, for our cost savings.